here this is the oven, and this is the probe. These are the two conducting probes, one and another, and these two probes are connected with this aluminum foil, and here the sample is placed, the dielectric sample, that is a ferroelectric material, ferroelectric ceramics. The plate of this sample, barium titanate, these are the this sample is placed between two probes, right? The sample is visible here.
Yes, sir.
Okay, so these two conductors are separated by the dielectric, right? So it will act as a capacitor. So the dielectric constant, it can be defined as the capacitance of this sample C over C0, that is the capacitance in the free space, right? So if we know the values of these dimensions, the thickness and the cross-sectional area, then we can calculate C0. Okay. Now these samples along with the probes, these are placed in the oven. So this oven is connected through this wire. Okay, this is the RTD sensor. So it will detect the resistance of the platinum. Okay, here in the situated in the oven, and the resistance over resistance versus temperature is calibrated already in this instrument. So they will detect the resistance, and corresponding temperature will be shown in this display in degrees Celsius. And this probe terminals is connected here. Okay, now I am switching on the setup. The setup is now on, but the oven is in the off position. So this is the button for the oven. Okay, and this is the capacitance meter. So directly the capacitance that will corresponding to the temperature, the capacitance will be displayed here. So this is the capacitance meter. We can directly measure the capacitance from this display. Okay, and this knob is for set temperature. So we can control the rise in the temperature by this knob. So the whole divisions 1, 2, 3, 4, 5, 6, 7. So the whole range is divided into 7 regions here. Okay. So now if I choose to rise in a very slow rate, then we will move very slowly. The temperature, we set the temperature very slowly. We will move the knob very slowly. But if we are willing to do it rapidly, then we will move fast. Then the temperature will automatically rise in a very greater rate. Okay. Now how to place the sample? So there is the spring. Okay. So we'll move the spring. We can move the spring, and with this spatula we can place the sample here. Okay. So we can place the sample here, and gently we'll release the spring. So the temperature is now 18.3 degrees centigrade if the when the oven is in off state. Okay. Now we are going to on the oven, and gently we'll move the knob, and this will be the indicator of this oven whether it is in on or off. though it is in on, it is the oven is in still off position, and this is the indicator as this is not glowing. Okay, now we are moving very slowly. Okay, some sound is coming, right? Some sound is coming. So until that we have to move gently, and the oven is now in on state. Okay, so this is the control portion. So we have to control throughout the experiment up to 150-160 degree temperature in a rate 1 degree per 1 minute. Okay, so one thing you have to remember, that if the temperature is very fastly it will increase, then the equilibrium will not establish with the oven and with the sample, because the temperature of the sample has to be measured, right? Not the temperature of the oven. But we have to give the time to establish the equilibrium with the temperature of the oven and the temperature of the sample. So we'll have to give the time. That's why that rate has to be set. Okay. And the corresponding capacitance will have to be noted. So for temperature 19.4, the capacitance is 499 picofarad. It is in the unit picofarad. We are increasing a little bit. Now the temperature has risen to 20.1 and the capacitance is 501 picofarad. So we have to control by the set temperature, and corresponding capacitance have to be measured. The part 1 is uploaded yesterday, the theory part, that is explained in that video. So check the website for part 1, the theory part. Any question? Now the temperature is 21.6 and capacitance is 501 picofarad. So for the purpose of the demonstration, we will set the temperature in a very high rate. Okay, but in the practical time we have to give the proper time to establish the equilibrium. Just for showing how it is changing, how the capacitance is changing, as the whole region, if I increase in a rate 1 degree per 1 minute, then it will take a long time, and that will be very monotonous for you, I think. So we set the temperature in a rate. Okay, so the blink is now stopped. And you can see the temperature is moving fast. So 23 degree temperature, capacitance 505 picofarad. (24 degree temperature, 507 picofarad. So the capacitance is also increasing with the temperature. And the blinking has started again. Now the oven is off, but the temperature will be increased for some time due to the thermal inertia. We are moving the set temperature again. And one thing you should remember, that the temperature must not fall. Okay, we have to set the temperature likewise the temperature at any point of time, it must not fall. Now the capacitance is decreased actually. It was 507 picofarad, but now it is 488 picofarad at temperature 37. As the temperature is moving very fast, this result is not so accurate, but we can see how it is moving, how it is changing. At 40 degrees centigrade, the capacitance is 481 picofarad. 481, 42, it is fluctuating. The temperature is now 44 and corresponding capacitance is 476 around. Can you read the display? Is it visible?
Yes, sir.
Okay. So the capacitance is now 472 in corresponding to the temperature 49 degrees centigrade. At 53 degrees centigrade, capacitance is 469 picofarad. So at 57, the value is 469. So with the temperature in this region, the capacitance is not changing much. Now at 74 degrees centigrade, the value is 476. So at 80, the value is 484 picofarad. '87, 88 degree temperature, and value is 499. So it is increasing, right? So at 100 degree temperature, the value is 531 picofarad now. So the value of the capacitance is now increasing very fast. So at 110 degree temperature, the value is 583, 84. It is 6:17 now at 115 degrees centigrade. At 120 it is 686 picofarad. The temperature is now 125 degrees centigrade and value of the capacitance is around 800. At 129 it has become 900 picofarad, around 900 picofarad. In this region we have to look very carefully. The capacitance is 936, 935 at 133.5 degrees centigrade. The value is fluctuating actually between 936 to 938. At 135 it has become 935. On 35.5 degrees centigrade and the value has become 932. So in this region the value is now decreasing. So at a point we have to find out that point of temperature at which the capacitance value start decreasing. So now the ceramics is not ferroelectric anymore. Okay, so it has become the paraelectric material, and the transition happens at a temperature that temperature is called Curie temperature. So we have to find out that temperature. Okay, so it is around 135 and 6 in this experiment, but roughly to demonstrate you have find out this, but this is not the correct value as we have increased the temperature very fast, right? So above Curie temperature the value is now 929 at 136.9 degrees centigrade. So around the Curie temperature range, so we have to take at an interval of 0.1 degree centigrade to find out the Curie temperature very accurately. Now see, the capacitance is decreasing. And it is decreasing very fast actually. So at 140 degrees centigrade, the value has become 860 from the peak value, right? So this is the experiment to find the dielectric constant. So how to measure the dielectric constant from the particular for a particular temperature? So we now we know the capacitance at the temperature of the sample, and we can calculate the capacitance in the vacuum from the specification of the sample, right? So we can take the division C over C0 and we will find out the dielectric constant at that particular temperature. So we'll plot it with the temperature. So in the x-axis there will be temperature, and the y-axis there will be the dielectric constant, and we have to find out at which point the dielectric constant start decreasing. So at that point will be called Curie temperature. So we have to find out the Curie temperature of the samples.